that, as you can see, with a little public health message. Do please follow all the precautions very strictly. It's the only way we're going to keep on top of this coronavirus. Anyway, moving on, lecture 5. We're now going to see some of the power of the Laplace transform, especially in relation to differential equations. We've had a bit of a dose of theory, now we're going to get some practice. But before we do that, we prove a really important result about how the Laplace transform handles the derivative of a function. And this is what makes it such a powerful tool to deal with differential equations. So suppose we have a function f of x, and suppose that its Laplace transform and the transform of the derivative converge. Interesting exercise. Think of an example for which the transform of f prime doesn't converge, but the transform of f does. Not very difficult. And suppose that f of x e to the minus px tends to 0 at infinity. Again, an exercise to think of an example for which this is not the case, but the function is nonetheless integrable. So suppose all of these things, and these are little technical conditions which we're not going to worry about too much in this course, but we know we need them. And all of this for the real part of p greater than p0, because as we know, Laplace transforms are defined on right-hand half planes. Then the transform of the derivative, f prime bar of p, is p times the transform of f minus f at the origin, pf bar of p minus f of 0. Absolutely fundamental formula which we're going to use again and again. And the proof is really simple. We just integrate by parts. The transform of f primed is the integral of f primed e to the minus px. Integrate by parts once, you get f e to the minus px between 0 and infinity. That's why we need f e to the minus px to vanish at infinity. And then we get 2 minus signs make a plus, one from the integration by parts and one from the negative in the exponential. And differentiate with respect to x brings down a p, you get p f bar of p, this term, minus f of 0 coming from the boundary contribution here. The transform of f primed is p f bar minus f of 0. Now, pretty clearly, we can iterate this to do transforms of higher derivatives, and you can do this by integrating by parts repeatedly, but there are other ways of doing it, and here's a simple way. Suppose we have the second derivative, f double prime. F double prime bar is p squared f bar minus pf of naught minus f primed of naught. And the way we prove it here is we put f primed equal to g, which amounts to starting with the derivative below for which we know the answer, and in a recursive process you put f primed is g, so f double primed is g primed, of course. Now you know g bar, that's pf bar minus f of 0. And then g primed bar, well, that's pg bar minus g of 0. And now you substitute in for g bar here, p times pf bar minus f of 0 minus f primed of 0 carries over, and that is p squared f bar minus pf of naught minus f primed of naught. So, an example. This is a very example-heavy lecture. This. Solve the differential equation f double primed minus 2f primed minus 3f equals e to the x positive, f of naught equals 1, f primed of naught equals minus 1. Of course, you can do this. You'll solve the auxiliary equation. You'll find the particular integral, a multiple of e to the x, probably, unless e to the x satisfies the homogeneous equation. You'll put together the general solution of the equation. You'll have two constants in it. You'll set up equations for f of naught and f primed of naught, and eventually you'll get there. Prelims question, very easy. But look at this. Suppose I take the Laplace transform of the equation. So I multiply by e to the p minus px, and I integrate from 0 to infinity. So what do I get? The transform of f double primed is p squared f bar minus pf of naught minus f primed of naught, minus twice the transform of f prime, minus 3 the transform of f, and that is equal to p squared f bar minus p plus 1, so that minus p is there, and the plus 1 is minus f primed of naught, minus twice pf bar minus 1, that minus 1 is f of naught, minus 3f bar, and the transform of the right-hand side, the transform of e to the x, is 1 over p minus 1. So if you simply tidy that up, you just got to collect together all the f bars. You've got one there, you've got one there, and you've got one there, 3 of them there, minus 3 of them. P squared minus 2p minus 3 times f bar, which is p minus 3 times p plus 1 times f bar. And then on the right-hand side, you get the 1 over p minus 1 you had before, and then you find there's a p minus 3 from everything else. So you divide through. F bar is 1 over p plus 1 plus 1 over p minus 3, p plus 1, p minus 1. Put this into partial fractions. So, for example, cover that up, put p equal to 3, and you get 1 over 4 times 2, 1 over 8, and 1 over 8 times p minus 3. Put p as minus 1, and you get another 8. Put p as 1, and you get a 4, so with a minus sign. So that's working out the residues in effect. I've just copied that over to this slide so we can see it. Now we just invert. We know how to invert all of these things. 1 over p plus 1 is e to the minus x, because remember e to the minus ax becomes 1 over p plus a. So 1 over p plus 1 becomes e to the minus x, and there are 9 over 8 of those because you've got 1 there and another 8th of them there. Plus 1 over 8 e to the 3x, the minus there becomes e to the plus 3x, minus a quarter e to the x. All right, maybe you don't trust me. Do a quick check. When you put x is 0, f of naught is f of 0, 9/8 plus 1/8 minus a quarter is 1, and f primed of naught is minus 1, which is what they should be. Always worth doing a little check like that if it's not too much hard work. And of course, p squared minus 2p minus 3, the equation that we had to solve to factorize, the quadratic we had to factorize here, is exactly the auxiliary quadratic. So we're not doing anything dramatically new here. What we're doing is we're doing it in a shortcut kind of a way. Now, maybe there's not so much to be gained here, because after all, you could have done this by elementary methods. But suppose I'd given you a 50th order constant coefficient differential equation. Or I'd given you a system, a 10 by 10 system, and systems like that arise very often in, for example, models of electric circuits. If you make a big model of the national power grid, you treat all the transmission lines as combinations of resistances and capacitances and inductances. Then when you write down the relevant equations, what you get is a whole lot of ordinary differential equations for the voltages at all the nodes where all the lines join up down at Didcot Power Station and at the edge of Oxford where our power comes in. And you want to solve all those and see what the states of the system are. That comes down to a huge, great constant coefficient set of equations. And one way of dealing with it is to hit it with a Laplace transform. And what it does is it takes the differential equation and turns it into an algebraic one. Back here we had a differential equation there, and it turned into an algebraic equation here. So you see, it's a great simplification. And then, of course, you have all the techniques of linear algebra to help you. Another example. Again, a trivial example. I've chosen very simple examples for these lectures, but you can find a more complicated version of this example. It's example 50 in the lecture notes and so on. This is 50a. Solve f prime plus f equals x with f of naught equals 1. Well, you know how to do this. There's an integrating factor and away you go. the integrating factor is clearly e to the minus x, and e to the x, and so you multiply by e to the x, and you'll have to integrate x e to the x on the right-hand side. What happens if you take the Laplace transform? Well, you get pf bar minus 1 from f prime, because f of 0 is 1, plus f bar, that's just the transform of f there. 1 over p squared is the transform of x. And so you tidy this up. F bar is 1 plus 1 over p squared. That's the 1 over p squared. Divided by p plus 1, the coefficient of f bar on the left. Put that into partial fractions. You can't do that by cover up because there's 1 over p squared, but it's a trivial exercise. And now you invert straight away 1 over p squared x minus 1 over p minus 1, 1 over p plus 1, e to the minus x, and there are 2 of those, and there is your answer. Here's another example. We've actually seen this one before. It was the impulse problem we saw in the motivation lecture 1. F double primed equals delta of x minus 1 with f of 0 is 0, f primed of 0 is 0. So if we think of f as being the position of a particle at time, well, call x time, so at time x, it starts off at rest at the origin, and then at x equals 1, time 1, it's given an impulse, and the impulse in this case is 1. All right, take the Laplace transform in x. F double prime just gives you p squared f bar because there's no initial condition. These two terms are both 0. Transform of delta of x minus 1 is e to the minus p, that's e to the minus px, evaluated at x equals 1. And so f bar of p is e to the minus p over p squared. Immediately invert this. 1 over p squared with the transform of x, and multiplying by e to the minus p says you need to take the function x and shift it by 1 and multiply by the heavy side of x minus 1. So you just take the function which is 0 and then x, and you move it along to the right by 1. And of course you saw that transform a little earlier on. Another example. This is a bit more tricky. It's quite a neat little example, this one. Solve f double prime minus f equals delta of x minus 1. So without the f there, if I cover that up, this is what we had before. But now I'm going to put in f double prime minus f, and I'm going to say I want f of 0 equals 0, and I want f to go to 0 as x goes to infinity. Now, this equation has a bit of positive feedback built in, because if you forget about the right-hand side for a moment, if you just said f double primed minus f is 0, that's the same as f double primed equals f, and that said that the acceleration is proportional to the displacement with a positive constant of proportionality, not like simple harmonic motion where it's negative, and so the further away it is, the more it accelerates. So we have an exponentially growing solution and, of course, an exponentially decaying one as well. But because we want f to go to 0 at infinity, we have to get rid of the growing one. So what that means is if there's no growing solution, and that means that f bar of p is holomorphic for the real part of p greater than 0, because the transform exists for all positive real p, because f of x goes to 0 at infinity. So if we take the Laplace transform of the differential equation, we'll say p squared f bar minus p times f of 0, well that's 0, but we don't know what f primed of 0 is. So what this problem really asks us to do is to find the value of f of 0 that makes f go to 0 as x goes to infinity. So there it is, f primed of 0, an unknown constant, minus f bar, the transform of f in the differential equation, e to the minus p, transform of the delta function. And so f bar of p is f primed of 0 plus e to the minus p, just taking that over, divided by p squared minus 1, p squared minus 1. Look at this. it has a pole at p equals 1. You can factorize the bottom, of course, p minus 1 times p plus 1. Has a pole at p equals 1 unless you make the denominator, the numerator, the one on the top anyway, f prime of 0 plus e to the minus p has to vanish at p equals 1, and then we'll have a removable singularity in which we have a 0 over 0, which we can use L'Hopital's rule to show is a removable singularity. And of course, you put p as 1 here, you have e to the minus 1, so f prime of 0 should be minus e to the minus 1, and so f bar of p is e to the minus p minus e to the minus 1 over p squared minus 1. And now I put this in partial fractions. This is the factor. And then the partial fractions are a half times minus 1 over p plus 1 over p minus 1. And that is the Laplace transform of minus the sign of x, because that's going to give you e to the x, and that's going to give you e to the minus x. And so you get minus the sign of x. So there you are. I've just copied that over to this slide so we can see what's going on. You now invert straight away. The e to the minus p tells you you've got to translate by 1. So sign of x minus 1, heavy side of x minus 1. And then e to the minus 1 to constant minus e to the minus 1 sign of x. And you can write this as minus e to the minus 1 sign of x if x is between 0 and 1, and minus e to the minus x sign of 1 if x is between 1 and infinity. And if you think that there's some structure here with e to the minus 1, e to the minus x sign of 1, you're right. This is, in fact, the Green's function for the differential operator f double primed minus f with 0 boundary conditions, as anybody doing differential equations 2 will recognize. It's not at all hard to check that this function is continuous at 1, because you put x equals 1, obviously those two are equal. And then if you work out the derivatives, f primed at x equals 1 and the limit as x tends to 1 from above and the limit as x tends to 1 from below, you will find there is a jump of 1, which is exactly consistent with f double primed is delta of x minus 1, and so on. And this is actually an interesting point. If we just go back to our differential equation, there it is. F double primed minus f is delta of x minus 1. So what this tells us is that f double prime has a delta function in it at x equals 1. F itself is continuous at x equals 1, is much less singular than the delta. Or to put it another way, there's a delta function on the right. There has to be something on the left that is also a delta function to balance that, because otherwise there would be a singularity equal to something that's smooth, and that would be like saying 1 equals 0. So the highest order singularity, which is the delta function here, has to be matched by something on the left, and that's always the highest order derivative, because, as you know, differentiating makes functions worse. So every time you differentiate, they become worse behaved, and so you differentiate twice, you'll get the most singular behavior of this f. There are, of course, a lot of higher order terms in f double primed and in f, and they come from the solution itself. From here, maybe is the easiest way to see it. There are a lot of higher order terms, but the leading order behavior, the most singular behavior, is a delta in f double prime. Now, we're going to have one more example, and then you might want to take your 20-20-20 break after this. And this is going back to your prelims work on the wave equation. So remember, the wave equation describes waves on a string, or one-dimensional sound waves, for example, sound waves going down a pipe, or light waves going down an optical fiber, all sorts of situations in which you have one-dimensional waves. And it says you have a displacement u of x and t, which if you're thinking of a string is just the displacement of a string up and down, and it satisfies d2u by dt squared. This is the acceleration is equal to c squared, the speed of sound squared, multiplied the wave speed squared, multiplied by d2u by dx squared. This d2u by dx squared is the restoring force that balances the acceleration. So this is just Newton's second law, that mass times acceleration is equal to restoring force. So we're going to do a semi-infinite string, x positive, and we're going to start with it having zero displacement and zero velocity. So it's sitting there waiting for us to do something. And then on the end, x equals 0, you have someone standing there, and what they do is they move that end up and down with amplitude f of t. So for t positive, they start waving that end of the string around, and what you expect is that a signal will propagate along the wire away from the bit you're moving at the wave speed c. And the question is, can we see that coming out of this problem? So there we are, there's the wave equation. There's the initial condition u of x and 0 equals 0, put t as 0. du by dt of x and 0 is 0. U of 0 and t as f of t is the boundary amplitude. So what we're going to do is we're going to take the Laplace transform in time. Now, what does that mean? It says u of x and t goes over to u bar of x and p, so we're going to integrate in time the integral 0 to infinity u of x and t e to the minus pt dt. So don't get confused because we've been using x here before, now we're doing it in the time variable. So if we go back to the differential equation, when we hit this with the Laplace transform, this is the second derivative, so we'll expect to see p squared u bar, and then some initial condition terms, but because we said that u and du by dt are both 0, those terms both vanish, so this is simply p squared u bar. And for this, on the right hand side, well, you just differentiate under the integral sign with respect to x, and you get c squared is just a constant, d2u bar by dx squared. So you just differentiate under the integral sign becomes the integral of d2u by dx squared, which is d2u bar by dx squared. And when you put x equal to 0, you have the transform of whatever amplitude you're putting on. So, if you want to solve this equation, p squared u bar is c squared d2u bar by dx squared. Well, you'll get e to the plus or minus x over c, because remember, p is a constant as far as this equation is concerned. C is a constant, so you take the c over there, p squared over c squared u bar there, d2u bar by dx squared there, and so the solutions are e to the plus or minus px over c. But of course, p is going to be positive. This is going to be a right-hand half plane for the Laplace transform variable p. C is positive, x is positive. So we cannot have the plus sign because that would give you exponential growth. So only the minus sign counts. And that means that u bar is actually just something times e to the minus px over c. And if you put put x equal to 0, u bar of 0 and p is f bar of p, you have u bar of x and p is f bar of p, e to the minus px over c. It may take a little while, it might be worth going through that calculation carefully, but at any rate, there is the answer. And now, of course, you can invert this immediately. U of x and t, we have e to the minus px over c, that tells us we've got one of these translation things. U of x and t is f of t minus x over c, so x over c is the translation constant. Just go back and compare it with the results we had earlier. So f of t minus x over c times the Heaviside of t minus x over c. And what is that? That is indeed the boundary signal f of t delayed by x over c. In other words, it's travelling out in the x and t plane. It's travelling along lines x equals ct. It's travelling along lines with speed c. And if you were to draw a diagram of the solution itself at a particular time, it would be whatever it is up to x equals ct and then 0 everywhere else. Now, of course, you can get this by the standard method that you already know. You just put the general solution of the wave equation, f of t minus x over c, and g of t plus x over c. And this tells you how to do it. That should be a capital G, of course. And the fact that capital G is 0 corresponds to having no incoming waves, and that corresponds to no exponential growth. Anyway, that's a little refinement, but you see how the Laplace transform let us solve that problem really very straightforwardly. Right, good chance for a 20-20-20 pause. And we come back for one more little bit of theory and a couple more examples. So we saw how to transform a derivative. Now we're going to see how to transform x times a function of x. If the Laplace transform of f of x exists, then the transform of xf, or xf all bar, is minus df bar by dp. So that's quite neat. Let's see how it works. You work out, let's start from the right-hand side here. Minus df bar by dp minus d by dp of f bar. Take the d by dp under the integral sign. F is independent of p. You only need to differentiate that p up there, and that brings down a minus x. And the minus kills the minus out the front there, and that is indeed the transform of xf. And there's a little aside here for those of you who want to worry about things, as you should, which is why didn't I need to state that the Laplace transform of xf exists? Well, this is going back to the exponential decay of e to the minus px, because if I have the Laplace transform of f for the real part of p greater than p0, then if I look at the Laplace transform of xf at a very slightly further to the right value of p, e to the minus p plus epsilon times x, rearrange the exponent so that it's x e to the minus epsilon x times f e to the minus px. This thing here is a continuous function which is bounded. It's bounded by quite a large bound, of size 1 over epsilon, but it is bounded. And that means that this integral exists, because you can take the bound for this bit of it out in front, and then you have something which you know exists because you know your Laplace transform exists. And if that's true for all epsilon positive, that tells you that your transform of x times f exists for all real p greater than p0. Another example. Invert 1 over p plus 1 squared. Well, of course, you know how to do this. We've already seen examples like this. We know that this is going to be 1 over p squared is the transform of x, so we know this is going to be x times e to the minus x because of a plus 1 here. But here's another way of doing it. 1 over p plus 1 squared is minus d by dp of 1 over p plus 1. And we know that 1 over p plus 1 is the transform of e to the minus x. So our function is x e to the minus x. All these are little Laplace transform tricks that will make your life very much easier when you're coming to doing actual problems. Another example, the transform of 1 is 1 over p, so the transform of x is x times 1 is just minus d by dp of 1 over p is 1 over p squared. And of x squared, you take this one and differentiate with a minus sign, minus d by dp of 1 over p squared, you get 2 over p cubed, and so on. So that's a neat way of doing that. The other way round, as it were, instead of starting with x to the n and working backwards, you start with x to the 0 and work outwards. Here's another example. Solve f prime plus fx, xf equals 0 with f of 0 equals 1. That's an easy problem. And deduce the Laplace transform of e to the minus x squared over 2. And that will tell you the moment generating function of a standard, the modulus, mod x, of a standard normal. So if you take a standard normal distribution, x, and then you take its absolute value, call that y is clearly a positive random variable, and its density function is just twice the density of the standard normal on the interval 0 to infinity. And this will give you the moment generating function of that random variable. Moment generating function of standard normal is just e to the t squared over 2. So what is the solution? The differential equation had the solution e to the minus x squared over 2. That's easy. You multiply by the integrating factor e to the x squared over 2, e to the integral of x dx, e to the x squared over 2. Now, and that you do by just elementary methods, but now you do it by the Laplace transform. So you get pf bar minus 1 from taking the transform of f prime, minus df bar by dp from the transform of xf, and that's equal to 0. And this is virtually the same differential equation. It has an integrating factor e to the minus p squared over 2 now. df bar by dp minus pf bar equals minus 1, so take that over the right hand side and that over the right hand side. df by dp minus pf bar is minus 1. d by dt p of this is equal to minus e to the minus p squared over 2. And then to find the solution that decays at infinity, you just integrate this. The solution that decays at infinity, what you'll do is you'll use infinity as one of your limits of integration, and what that will do is it will make automatically the function go to 0 when the other limit of integration, which has got to be p, tends to infinity. So you don't have to do any arbitrary constants that way. You just build in the boundary condition via your limit of integration. And by putting p as the lower limit, you automatically get this minus sign sorted out too. So f bar of p is e to the p squared over 2, which is this one taken over to the other side, the integral from p to infinity, e to the minus s squared over 2 ds. And that might not have been so easy to get. You can do it from the definition of a Laplace transform by completing the square, but it's quite hard work, whereas this was really very simple. You might ask, given that this function grows extremely rapidly as p goes to infinity, whether this product does in fact vanish as p goes to infinity. Because although this goes to 0, does it go to 0 fast enough compared with this one? And the answer is yes, it does. And the easy way to see it is to write this as the integral divided by e to the minus p squared over 2. And then you can use L'Hopital's rule once on it, and you will find that the limit is indeed 0. So we're going to end this lecture with another example, and this is quite a lot more difficult in the sense that it's not obvious how you can do it by an elementary method. There is in fact an elementary method, but you won't have seen it yet. And so this is an example at the moment where the Laplace transform is essentially your only way of getting the solution. So what is this example? We're going to solve the heat equation. du by dt equal d2u by dx squared. So we're modelling heat flow in a semi-infinite medium, x positive for t positive as well. And we're going to start off with 0 temperature everywhere. And then we're going to raise the temperature at x equals 0 at the end of the bar. We're going to raise it to 1. So you might imagine this is a model for the temperature in a very thick piece of material, and you want the temperature at one end to be 1, and the question is, what is the heat flux into the material as a function of time that will let you do that? So you want the temperature to go from 0 to 1 instantaneously, so obviously something quite singular is going to happen, and you want to find out what flux is needed to make that happen. So how do we do this? We take the Laplace transform in t, so we define u bar of x and p like we did for the wave equation, the integral 0 to infinity u of x and t e to the minus pt dt, so we're integrating in t, and we require this to decay to 0 as x goes to infinity because we started off with 0 heat in this bar, and you can't get the temperature at infinity to get up to any value other than 0 in a finite time. So we want u bar to decay to infinity because u goes to 0 at infinity as well. So what does that give us? The transform of du by dt is pu bar minus the initial condition, which is 0. This is that 0 there is u of x, and 0 is 0, the initial temperature in the bar for all x. So du bar by dt is pu bar minus 0 equal d2u bar by dx squared. And u bar of 0 and t is u bar of 0 and p, but this is the transform of 1, which is 1 over p. Well, the solution that's bounded at infinity, provided you take a sensible choice for the branch of the square root of p, is something a of p, some function, some multiple of p, e to the minus x root p. And then if we take the transform boundary condition, we find that a is 1 over p, so u bar of x and p is e to the minus x root p over p. And so du bar by dx is minus root p. That minus root p comes from the exponent here, e to the minus x root p divided by p. Now you put x equal to 0, and you find that g bar of p is 1 over root p. Remember, there was a minus sign in the definition of g here. Minus du by dx is evaluated as x equals 0, and that kills this minus sign here. The root p and the 1 over p turn into 1 over root p, and e to the minus x root p, when you put x at 0, just becomes 1. But we recognize this. We know that if you take the transform of x to the alpha, or I should really say t to the alpha here, you get gamma of alpha plus 1 over p to the alpha plus 1. So we just turn this round. What is the function that transforms to give you 1 over t to the half? You need to put alpha as minus a half, and you get g of t is 1 over gamma of a half. That's minus a half plus 1 is a half. T to the half minus a half plus 1 is a half. But gamma of a half is root pi, and so we have 1 over root pi t. And as I say, that is a result that I don't think you could have got by any other method that you yet know. We'll stop there. We have seen a large number of examples of the Laplace transform. Next time we're going to look at two really famous theorems about the Laplace transform, the convolution theorem and the inversion theorem, and we're going to see a whole lot more examples. So I'll look forward to seeing you then.